Travis. Hello, Wayne. This is John Whitaker for the Probability Graduate Level class, and this is our 21st video lecture. And today we want to talk about conditional variance and also look back at something about the compound random variable, conditional variance being involved. And so let's start off today with the definition. So the conditional variance of x given y equal to y is denoted by it's variance of x given y equal to y, and is defined by the conditional variance of x given y equal to y is equal to the expected value of the quantity x minus the expected value of x given y equal to y, that part to be squared, okay, given y equals to y. So it's the expected value of the quantity, x minus the expected value, the conditional expected value of x given y. Whatever that is, you square it. That's a random variable. And then you take the conditional expectation of that, given y equal to y. That's its definition. Well, as we have with the regular variance, we have a formula. It may be easier to use. We'll do an example where we'll use this one in just a second. But here's a formula. So as a fact, the variance of x given y equal to y is equal to the expected value of x squared given y equal to y minus the expected value of x given y equal to y to b squared. Very similar looking to what our formula was for just the regular variance for random variable. Conditional variance. We have it back here. The proof will break down into cases, but first we'll say by the definition the variance of x given y equal to y is equal to the conditional expected value of x minus the expected value of the conditional expected value of x given y equal to y to be squared given y equal to y. So case 1 is where x and y to both be discrete random variables. Okay. So we're looking at this expected value here. All right. The first thing we'll write is the expected value of the quantity x minus the expected value of x given y equal to y. That to be squared given y equal to y. We'll square this out first. What we do, we're talking about conditional expectation of x squared minus 2x times additional expectation of x given y equal to y. And then plus the conditional expected value of x given y equal y, that quantity to be squared, given y equal to y. Okay, so we have discrete random variables involved. And so we're taking the expected value of a function, a random variable, of y given y. So here, what we'll think of is this is a function of x. That's what we'll think of. So this is going to be random variable x. So this is the sum, okay, over all possible x values. And what I write is x squared minus 2x times the expected value of x given y equal to y. Remember, that's a random variable of this function y. Plus, here, we leave this as is, b squared, that times the joint, the conditional PMF of x given y, x given y. That's what we have. Okay, that's equal to the sum, so we break this up into many sums, over the x's of x squared times s of x given y, x given y, minus, so here's a sum, over the x's of 2x expected value, x given y equal to y, times this conditional PMF. And finally, we have plus the sum over all x values, expected value of x given, conditional expected value of x given y, this to b squared, s of x given y. Working with this quantity. And this is equal to the first sum that we had over there is nothing more than the conditional expectation of x squared given y equal to y. Minus, the next sum had some constants with respect to x. Particularly, we pull out the 2 in the conditional expectation of x given y equal to y, because that's a function, a random variable is a function of y. And then we have the sum over the x values of x, f of x given y. And then the last sum, and that was a minus, so last sum, the conditional expectation that was being squared can be pulled out in front because it's a constant. And here, this is the sum over the x value of the conditional PMF. Of x given y. So this guy was part of what we said the result was. That's good, we're going to leave it alone. This is minus 2 times the expected value of x given y equal to y. Here, this is the conditional expectation of x given y equal to y. Plus this sum, plus this expected value, conditional expected value, e squared. And then lastly, this sum, I'm going to say, is the sum over all x's. Here, this is nothing more than f of x comma y over f sub y of y. Remember that. This first part I'm leaving alone. Write it down. Here, this is 2, and then we have the conditional expectation of x given y. Multiplied by itself, so that's the b squared. Here, this is plus, this is the expected value of x given y equal to y. Here I can pull out the 1 over f sub y of y, and this is the sum over all x values of f of x comma y. I'm taking my time there. Again, this is the expected value of x squared y equal to y minus 2 times the expected value of x given y equal to y to be squared. Here, this is plus, I made a mistake, this is supposed to be squared. So the conditional expectation of x given y equal to y to be squared, and then this is 1 over the PMF of y. And here, when I sum up over all x values of the joint PMF, what I get is the PMF of y. So those two cancels, and we're left with the expected value of x, the conditional expectation of x squared of y given y minus 2 times the expected value of x, y equal to y, plus, well, I forgot to square again. The conditional expectation, here's the square that I forgot again. The conditional expectation of x given y equal to y to be squared. And of course, these are like terms, so what we end up with is exactly the result we wanted. Let me write it over here. That's equal to the conditional expected value of x squared given y equal to y minus the expected value of x given y equal to y, that quantity to be squared. And that's what we wanted to get, but this was just in the discrete case. Now, for the case when if x and y are both continuous, the proof is analogous to case 1, and will be left to the students, you guys, to do. So that proves the fact that we have, gives the idea for the fact for what we have for the formula for conditional variance. I'd like to do an example of that next. Before I do that example, I said case 2 is analogous. Of course, it will involve integrals instead of summations. Okay. So as an example, we're going to let x and y be discrete random variables with joint PMF given by the following table. Okay, so here are the x's, here are the y's. So the x's are down here. 1, x values are 0, sorry, and 1, and the y values are 1, 2, 3. And so here's what I have. 1/8 for the joint PMF when x is 0 and y is 1. That's the way that's read. And this is 2/8, and this is 1/8, and this is 2/8, 1/8, 1/8. So here's the directions. It says find the conditional variance of y this time when x is equal to 0. So here, just as a quick note, the variance using our formula of y given x is equal to 0, that's the same thing as the expected value of y squared given x equals to 0 minus the expected value of y given x equal to 0 to b squared. I've got to compute each one of those. Now, the expected value of y given x equal to 0, that's equal to, well, this is conditional expected value, so it's the sum over all y values. Well, what does y run from? It runs from 1 to 3 of y, and then here's the conditional PMF of y given x, but x is 0. And so I got to find this conditional PMF. So here, f sub y of x, y given 0. Remember what that is. That's f of 0, y, and then here it would be f sub x of 0. That's its definition. Note that. Well, f sub x of 0, so how do I find f sub x of x? It's the sum over all y values, so it's 1 to 3. Here it would be f of 0, y, which equals to f of 0, 1 plus f of 0, 2 plus f of 0, 3. Look back at the chart. X is 0. What this ends up being, so I'm looking at the chart, 1/8 plus 2/8 plus 1/8. And it ends up being a half. So, this conditional PMF of y given x, y given x equals 0, is equal to f of 0y over 1/2, which equals to 2 times f of 0y. So remember what we're trying to compute. We're computing I made a mistake over here. What am I trying to compute? I'm trying to compute the expected value. It should be y squared given x equals 0. So here's a y squared is what I should put here. So make those changes. I made a mistake. Okay. So the value of y squared given x equals 0. Now, if we want in this sum, as y runs from 1 to 3 for our problem, of y squared, and here I have f of 0y times 2. And so this is equal to, so it would be 2 times 1 times f of 0, 1 plus, it would be, when 2, we have 4 times 2, f of 0, 2 plus, then it would be 9 times 2, f of 0, 3. Now, I've erased the chart. But that's equal to, okay, this is 2 times f of 0, 2, so 0, 2, let me see what the chart was, it was 1/8. Plus, this is 8, f of 0, 2 was 2/8. And then, plus, this is 18, f of 0, 3 by our chart is 1/8. So this ends up being 6, so it's 2, it's 20, it's 36 over 8. 4 goes into both of these. And so what we get is 9 over 2. That's what we get for that part. Remember, our job is to find the conditional variance. Now, in the second part for the conditional variance, we have the expected value of y given x equals 0. We need to know what it is, because we've got to square it. And so here, that's going to be the sum over the y values, and y runs from 1 to, and I had written that before, but it's okay, I want to find the y squared. Y runs from 1 to 3 of y, f of x given y given x. Here's y given 0. We found that part. So that's the sum. Y runs from 1 to 3 of y times 2. And here it was f of 0y. And so that's going to be equal to, so 2 times, when y is 1, we just get 1. 2 times 1, f of 0, 1, plus 2 times 2, f of 0, 2, plus, then it would be 2 times 3, f of 0, 3. And so, we'll complete that over here from the chart, and we actually already found those numbers. We get that this is equal to 2, and f of 0, 1, 1/8, plus, here it was 4, I think, and then we get 2/8, and then again here we have, was, I think 6, and then 1/8. Okay. That ends up being, let's see, so 2, 8's 10 is 16 over 8, 2. So, the conditional variance of y given x equals 0. Remember, the expected value of y squared given x equals 0 minus the expected value of y given x equals 0 to b squared. And so when we put in our values for that, this was 9/2. I think it was 9/2. Yes. Minus, this is 2 squared, so that's 4. So this ends up being 9 minus 8 over 2, which is 1/2. That's our answer. That's that example. Let's do another example where we're talking about continuous random variables. suppose x and y are continuous random variables with joint PDF, something we've looked at before, f of x comma y is equal to, okay, so it's 12x if 0 is less than y is less than 2x is less than 1, and it's 0 otherwise. Okay, and so here, what we want to do, in this case, we want to find the variance of x given y equal to y. So when I look at this, by definition, the conditional variance of x given y equal to y is equal to the expected value, conditional expectation, of x squared given y equal to y, and then it's minus expected value of x given y equal to y to b squared. Okay, so we've got to find each one of those parts. Now, the expected value of x squared given y equals y, what is that? That's going to be an integer. So it's equal to an integer. Minus infinity to infinity. X squared is conditional PMF of x given y. Given y. And now, integrate that with respect to x. Okay, so note again, f of x given y of x given y is equal to f of xy over f of x, f of y of y. So I've got to compute this. MF, the PDF of y. So f of y and y, that's the integral from minus infinity to infinity of the joint integrated with respect to x. Now, look, that joint is 0 a lot of the places. So here, if I draw underneath in the xy plane, remember I'm looking at it. Is 0 is less than y is less than 2x is less than 1. So 2x is between 0 and 1. So that means x is between 0 and a half. And y is between 0 and 1. We've looked at this before. And that's what we have in this region. That's what we have. So we've done this before. This is equal to 8x. I'm sorry. So that's what you do. But we found this before. Previously, so I'll just make note of that. We've worked with this before. F of x given y, x given y, is going to be equal to, so here's what we've got. It's 8x over 1 minus y squared. That's what it is. With some restrictions. Okay? And the restrictions can be found by here. For whatever y is, look what the x's run from. So the x's here will run from this line, which is y over 2, x equal y over 2, to this line, which is x equal 1/2. So, and otherwise it's defined to be 0. So here that affects this integral. So the conditional expectation of x squared given y to the y is equal to this interval. So it's from y over 2 to 1/2 of x squared, and here I'm going to put 8x over 1 minus y squared dx. That's where we are. Okay, so that's equal to, well, the 1 over 1 minus y squared can be pulled out. And then we're having 8x squared, 8x cubed. So 8x cubed. So it's antiderivative, 8x to the 4th over 4. We want to evaluate that from y to 2 to 1/2. So here, this is equal to, you'll forgive me, this is 2x to the 4th over 1 minus y squared. Evaluated as x runs from y over 2 to x being 1/2. Okay, if I stick in 1/2 first, it's 1/2 times the 2, that eliminates each other. I'm left with 1 over 8, because it's 1/2 to the 3rd power. Times 1 over 1 minus y squared. Minus, now again, I'm going to get the 1 over 8, because when I stick in y squared, y over 2 and raise it to the 4th power, the 2 is raised to the 4th, but it's got a 2 in front, so that makes 8 in the bottom. Here's y to the 4th, and then this would be 1 minus y squared. So we end up getting 1 over 8 times 1 minus y squared, and they have the same denominators, and it's minus y to the 4th. Now that can be simplified. So the simplification for this is 1, so it's 1 minus y squared times 1 plus y squared, so it's 1 plus y squared over 8. And here we should have some restrictions for what y can be. And so y runs from 0 to 1. Now, we need to find the second part of the quantity involved of our formula for the conditional variance. And so here we need the conditional expectation of x given y. So that is an interval again, from minus infinity to infinity of x, and then it would be f of x given y dx. And as we had before, it's going to be an interval from y over 2 to 1/2 x, this was, I believe, from our previous word, 8x over 1 minus y squared dx. When I integrate this, I pull out the 1 minus y squared. The x squared, 8x squared, its antiderivative is 8x cubed over 3. I need to evaluate that from x equaling y over 2 up to x equaling 1/2. And so here, when I stick in the 1/2 cubed is the 1/8, so we get 1 over 1 minus, or there's 3 out front, y squared, then minus, when I stick in the y over 2, I get y cubed over 3 times 1 minus y squared. So here this is 1 minus y times 1, it's plus y plus y squared, all over 3 times 1 minus y times 1 plus y, and so that simplifies as 1 plus y squared over 3 times 1 minus, or it's 1 plus y. That's what we get. And again, this is where we have y runs from 0 to 1. So, the conditional variance of x given y in this problem is nothing more than the conditional expectation of x squared given y equal to y minus the conditional expectation of x given y equal y to b squared, and that's equal to, so for each one of these parts, we found it to be 1 plus y squared over 8 minus, it would be 1 plus y squared to b squared over 9 times 1 plus y to b squared. And that's as far as I'll simplify it. There's two more things I want to do. And the first is analogous to where we had a fact relating the expected value of a random variable to conditional expectations. And so here we're going to have the following fact. It's called the conditional variance formula. And it says the following. It says the variance of x is equal to the expected value of the conditional variance of x given y plus is the variance of the conditional expectation of x given y. So we want to prove this. So we're going to look at each part. So here, note the variance, we're going to start off with that, or the expected value of the variance of x given y. Well, that's equal to, so we've learned a formula for the conditional variance. So this is the expected value, it's equal to the expected value, that's this guy, of the expected value of x squared given y minus the expected value of x given y to b squared. All right. Now, these are, we think of them as random variables, y. And so this is the, we're subtracting them, and the expected value of subtracting is the expected value of the first guy minus the expected value of the second guy. Now, let me write up here. The expected value of the conditional expected value of x squared given y, that by previous fact, extension of the previous fact that we had, yields the following. This is the same thing as the expected value of x squared. Okay. That's equal to x squared. And then similarly, this is minus well, I'll just write it down as the expected value of the expected value, it's not simple, of x given y to b squared. And this is by this fact, the expected value since the expected value of g of x given y, the expected value of that. Okay. So we had a fact that the expected value of x given y, that's nothing more than the expected value of y of x. So here it's analogous to the expected value of g of x. And that's what I'm using to make the replacement here of the expected value of x squared. Now, so that was part of what was involved in our formula. The second part that's involved is the variance of the expected value of x given y. So this part so using our variance formula, just for variance of something, this is going to be equal to the expected value of x given, the expected value of the random variable, expected value of x given y, to b squared in that form. And then it will be minus, this will be the expected value of what we have here, the expected value of x given y, all that to b squared. That's what this formula is. So here, that's equal to, I'll leave this part alone, minus, but of course, the expected value of the expected value of the conditional expectation is nothing more than the expected value of x. And that's to be squared. So in our formula, we're working, for the fact, we're working with those right-hand sides. We're trying to show that that's equal to the variance of x. So, from that right-hand side, what we had was the expected value of the variance, conditional variance of x given y, plus the variance of the conditional expectation of x given y. That's what we said the answer was to the variance of x. Well, we computed what this was. I'm looking at it. It's equal to. So it's the expected value of x squared minus the expected value of the expected value of x given y, that to b squared. That's that part. Plus what? This part was the expected value of the expected value of x given y to b squared. Ha! So those two things will cancel each other out. And then it is minus the expected value of x to b squared. So that's nothing more than the expected value of x squared minus the expected value of x to b squared, which equals to the variance of x. So there's the proof of that fact. Okay. Last thing I want to do in this lecture is give a fact about that compound random variable. Here's the fact. It says let x be a compound variable where x is equal to the sum, as I run from 1 to big N, of x sub I, and thus don't forget, and the x sub i's are independent and identically distributed with the expected value of x sub I equal to mu, and the variance of x sub I being some finite number sigma squared, and the x sub i's are independent of N, then the variance of x is equal to sigma squared times the expected value of N, and then it's plus mu squared times the variance of N. So that's our formula for what the variance of x is. Let's prove that. We've given the formula for the expected value of x for this compound random variable, so now we're doing it for the variance. Okay. Here's the proof. Well, the variance of x is going to be equal to, by our previous one, the expected value of the variance of x given N plus the conditional variance of the expected value of x given N. Now, we'll look at each part. So the variance, we'll look at this part first. Parentheses there. The variance of x given N, so we got a formula for that. It's the expected value of, well, of x squared. So that's the sum of the x sub i's. I running from 1 to big N. And to b squared, given, I'll say N, equal to N, then it's minus the expected value, sum as I run from 1 to big N, of x sub i's, given n equal to little n, all that to be squared. Okay, so that's this part. Now, this is the same thing as the expected value of this first part, so I'm going to write it down, except we know that n, again, is equal to little n. So here, the expected value of the sum as I run from 1 to little n of the x of i's to b squared, given n is equal to little n, okay, minus, now we've already done work here. And with this, and so what we found this to be previously would be n times mu, so that's b squared, because we said it was n times the expected value of x of 1. We did that previously. Here, this is equal to the expected value. Okay. So this will be x1 plus x2 plus all the way up to x sub n, given n equal to n. Well, I made a mistake. Times x1 plus x sub n, given n equal to n, minus this n squared mu squared. Now, when we multiply that out, so we have the expected value, well, we're going to have sums as I run from 1 to n of the xi squared. So that's some of the terms that we'll get. You know, x1 times x1, so that's x1 squared. Then we'll have x2 times x2 squared. Some of them. And then we're going to also have a sum, a double sum, as I runs from 1 to n, j runs from 1 to n, j being different than I, of xi, xj. Okay, so there's guys like that. Given n is equal to n. And then minus n squared, mu squared. Now, it turns out that if you have the expected value of one thing plus another thing, the conditional expected value, then that's the same thing as the conditional expected value of the first guy given n equals to n, plus the conditional expectation of the second guy. So it's this double sum. J from 1 to n, j has to be different than I, because if they're the same, you're here. xi, xj, n equal to n. And then again, we have this minus n squared mu squared still hanging around. That's equal to okay, so here we'll leave this as is. Well, I'm sorry, we won't leave this as is. We'll work here using independence. So what we'll get is this is the expected value of the sum of some independence. As I runs from 1 to n of xi squared. That's what that is. Plus here we have, due to independence again, the expected value of this double sum being different than I, minus n squared mu squared. This part here is due to independence between the x of i's and the n, okay? And the same thing here. And this part right here was due to the fact that I'm telling you the expected value of x plus y given z is the same thing as conditional expected value of x given z plus conditional expected value of y. Okay, the expected value of sum is the sum of the expected values. I runs from 1 to n. Here, this is a bunch of sums, so I can still bring the expected value inside. J is equal to 1 to n, but different than I. Expected value of x of I times x of j minus n squared mu squared. What I'm going to do next is, look, the x of i's are all identically distributed, so the expected value of x of 1 squared is the same thing as the expected value of x of 2 squared, and expected value of any x of whatever squared. So I'm just going to put them on one particular thing. The next thing I'm going to do is that the x of i's and x of j's are different. And so they are independent from each other. And so the expected value of multiplication is equal to the multiplication between the expected values, and that's what I'm going to write next. And then just here is going to be left as is. So that's going to be equal to, as I said, so what I'm going to write here is this is really the sum as I run from 1 to n of the expected value of x of 1 squared. And then plus here is the double sum and this is going to be the expected value of x of I times the expected value of x of j. I and j are different. And then this minus, we got n squared mu squared. Okay. So here we're having the same thing summed up a bunch of times. So that's n times the expected value of x of 1 b squared. Plus, here these are exactly the same thing, and they're mu. And so this is mu squared. And the question is how many of them do we have? So think about that multiplication. How do we get these guys? Well, what we do is we have x of 1 plus x of 2 all the way up to x of n, that quantity, times x of 1 plus x of 2 all the way up to x of n. And what you do to get some odd ones is you have x of 1 times x of 2. And then later you have x of 2 times x of 1. And your question is how many of those types do you have where they're not the same? And we've answered this before. Okay? And other types of, and so like the strong law of large numbers. And so here's what we have. What you're doing is you're taking two different ones. So how many of them do we have to choose from for the random variables? We've got n of them, and we're choosing 2 of them. And for each one of those pairings, let's say x of 1 and x of 2, we got 2 terms of that type. So we've got x of 1 times x of 2, and we got x of 2 times x of 1. So we have to multiply that by 2. There's the mu squared, and here's minus n n squared mu. So here, this is n times the expected value of x of 1 squared. Here, this is plus. These 2's are going to cancel out when we expand the n choose 2. And we're going to be left with n times n minus 1 times mu squared minus n squared mu squared. That's n squared mu squared. That's going to cancel that. So we end up getting n times the expected value of x of 1 squared Here I have minus n mu squared. Okay? And so these two things I said would cancel out. Okay. So this equals to n times the variance, because this is the expected value of x to b squared, of x. That's what we have. Okay? Of x sub 1. That's what we have. And so that's equal to n times sigma squared. So here's what I've got. What I've just shown is that the variance of x, the conditional variance of x given n, is really n times sigma squared. Now, in our formula, okay, where we're trying to compute the variance of a compound random variable, we had the variance of x is equal to, okay? And in our formula, we had the expected value, okay? Remember, let me get back to it. It's using that conditional formula for variance of x. So it's the expected value of the variance of x given n. So here, this is the variance of x given n, the expected value of the variance of x given n is equal to the expected value of n sigma squared, which of course is just equal to sigma squared times the expected value of n. That was part of our answer, our formula, for what the variance of x was. Not that far off. So the other part, remember, we need the variance. We need to be working about that variance. Of the expected value of x given n. So I'll just look at the expected value of x given n. Okay? And we worked with that before. This is the expected value of the sum as I run from 1 to n again of x of I given n equal to n. Okay. Which equals to, I'm going to shorten this down, it's equal to n times the expected value of x sub 1. We did that before. Which equals to n times mu. So I need to take the variance of this. So the variance of the expected value of x given n, additional expected value, is equal to the variance of n times mu. And let me work with that just for a second. Remember what that's going to be equal to. That's equal to the expected value of it's n mu to b squared minus the expected value of n mu, these are constant, all that to b squared. And so I can square this out, take its expected value, and so this is the n mu squared can be pulled out of the expected value. The expected value of n squared, and then this, we pull out the mu and it's got to be squared outside, and this is the expected value of n to b squared, and that's equal to mu squared times the variance of n. And so essentially putting everything together, we get the formula, we get the answer. Do that over here. So to summarize, here it is. So the variance of x, what we're talking about a compound random variable, remember what it was equal to. It was equal to the expected value of the variance of x given n, and it was plus the variance of the expected value of x given n. We just found these things. So here, this was sigma squared, I think. We did it earlier. It's sigma squared times the expected value n. So this was the expected value of n times sigma squared. That's what we had. Plus, this part we did completely just a second ago. And it was mu squared times the variance of n. And so that's equal to sigma squared times the expected value of n plus mu squared times the variance of n. And that's what we wanted to show. Okay, gentlemen? That's enough for today. Thank you very much for your time and patience.